Continuation marks are a feature you should expect to find in a virtual machine as a target for high-level programming languages. It's along the same lines as things like closures and objects, support for a call stack, or more generally continuations, tail calls, and control operators for manipulating the continuation. Continuation marks are not as well known, but they've been in Racket for a couple of decades, where they're an important building block for things like dynamic binding and exception handling. We've never explained before how continuation marks can be implemented in detail, and that's what this paper does. It shows how to add marks to an efficient implementation of control with first-class continuations. And specifically, we start with SHA-Scheme, which provides state-of-the-art performance in this area. We find that by adding support for marks, we can speed up mark operations by a factor of 20, which means a 10 to 25% performance improvement in real Racket applications running on top of SHA-Scheme. The talk will explain continuation marks, provide a refresher on how to implement continuations efficiently, and explain how to integrate marks into that implementation.
Non-volatile memory such as Intel 3D XPoint allows programs to persist data using regular writes with low overheads. However, ensuring that the data is persisted in a correct recoverable order requires persist operations which suffer from high latencies. Persistent transactions can alleviate some of this overhead, however they are hard to implement efficiently. Hardware transactional memory could allow us to do it, but it's incompatible with persist operations. Prior works try to get around this limitation, however they suffer from added latencies or they require modifications to hardware. Crafty uses existing commodity hardware transactional memory and combines it with persistence using a novel logging method. Crafty offers higher throughput and lower overheads for low contention programs.
Tradition dictates that a call stack is allocated in a large, fixed-size region of memory to provide the most efficient function call and return. However, modern languages need to support more advanced control flow mechanisms like coroutines, exceptions, and concurrency. These features place unique demands on the strategy chosen to manage the stack. So a language implementer may wonder, what is the best strategy for my compiler? Unfortunately, the current literature does not provide clear guidance. Previous studies suffer from various flaws in methodology and are outdated for modern hardware. Our work attempts to remedy this situation by providing an apples-to-apples comparison of 6 different approaches to implementing call stacks, using a single compiler and runtime system. We compare sequential performance, suitability to support advanced control flow mechanisms, and the overall complexity of their implementation.